Just as with vectors, we can add matrices and we have a way to scalar multiply matrices. Let's define what these are. Pretty much exactly the same as with vectors. So if A and B are both m by n matrices, their sum, let me put a little squiggly line under there, is the matrix A plus B written using that formula notation Aij plus Bij. So in other words, the ijth entry of A plus B is the ij entry of A plus the ij entry of B. I know I haven't done this all the time, but I want to double box this just because I do. Now, so a couple of examples. So this matrix plus this matrix is equal to, well, I have 1 plus 0 is 1, 2 minus 1 is 1, 3 plus 2 is 5, 4 plus pi is 4 plus pi, 5 plus 0 is 5, and 6 plus 6 is 12. On the other hand, if I wanted to do this plus this, that's undefined. That's because the two matrices there do not have the same size. So this is undefined. So now let's move on to the definition of matrix scalar multiplication. Definition. If A is m by n and C is any scalar, then we write the scalar multiple of C and A is CA equals C times Aij, or equivalently, in other words, the ij entry of C times A is C times Aij. And again, let's go and box this guy. An example. Well, I could just do 3 times 0 minus 1, 2, pi 0, 6 equals 0 minus 3, 6, 3 pi 0, 18. One can then go ahead and define what it means to take minus a matrix, and that's the same way that we defined it for vectors, and we know what to do with A minus B. And we have our zero matrix, which we've already talked about in the previous video. And you can even go and ask whether these satisfy the same properties as with vectors, and it turns out they do, and that is theorem 3.2 from the book.